All right. So, hello, my name is Charles Shin. I'm from China International. And the topic I'm going to talk about today is called pharmacokinetics, and I'm going to discuss about the basics and the mathematics behind it. So, it's an introductory class, like 101, for the university students. So please don't be stressed out. It's going to be very simple and also quite elegant. Before we start, we need to understand the very definition of the pharmacometrics, which is the broader family or branch of pharmacology or like pharmacokinetics. So the definition of pharmacometrics is a quantitative analysis of interactions between xenophobics, which are drugs that are foreign to our body, and the patient themselves. It belongs to pharmacology, and also it bases off from two models. First is pharmacokinetics, which is the study of the drug concentration inside your body for a certain amount of time. And second one is pharmacodynamics, which is the relationship between the concentration of the drug and the effect that it has. Because as we all know, drugs all have their own unique effects to our body. So the primary variables we have to focus on whenever talking about pharmacometrics and also pharmacology in general is the dose, concentration, and also the effect. We're going to use the mathematical models later in order to understand the specific term called pharmacokinetics. So what is pharmacokinetics? Let's go to the basics. So in Greek terminology, it is a combination of two fragments. It is pharmakon, which is a drug, and kinesis, which for many of you, including those who majored in chemistry, would know that it's a movement. So pharmacokinetics, by the very definition, is the study of the rates of absorption, distribution, metabolism, and excretion of drug and its metabolites. So it applies to multiple models, for example, statistical moments for those who are taking AP stats or other college level stats. And also it does some sort of exponential modeling, and physiologically based pharmacokinetic model, which is also called as PPPK model. And some of these terminologies will be familiar to you once you go to college or once, I don't know, you are in middle school. So it's very basic. There are multiple branches in pharmacokinetics. So I've chosen three out of the three big ones out of all of the branches. First one is toxicokinetics, which is the pharmacokinetics of all substances that are toxic, that are at a toxic dose, because there may be, it really depends on the drug. Like in some drugs, like chemotherapy drugs, really need tight regulation in terms of having an effective dose, which is appropriate and safe and also effective, but yet not lethal to the people, because as we all know, your body sometimes give in, but also sometimes has to give out. And there's a branch called clinical pharmacokinetics, which is the application of therapeutic management. This is often studied by in situ wet lab people who does these kind of therapeutical drug approving it by looking at how it does in the laboratory, for example, like mice or guinea pigs. And the last one is called population pharmacokinetics, which is also called POP-PK. It's a statistical estimation of the unknown population distribution. So it's quite non-linear because it fluctuates. So that is also like mathematically averaged out, that range of error, in order to understand the validity of the model. So why are we discussing all the pharmacokinetics? Because this technically KGSEA is a math organization. So why are we going to discuss about pharmacokinetics? So for this one view, rather than focusing just on the pure mathematics, we're going to also we want to have a broader picture of what it means for the drug to enter our body and be excreted out. Now, this is just one part of a very complex movement that the drug does inside our body. Remember, pharmacokinetics is the movement of the drug. So this is slightly a more expanded version of what you need to know about pharmacokinetics. Well, as you can see in the visually, you know that there's a lot to memorize. So as I said, this is a very introductory class, and this is just like in Korean term, it's also called you just lick the surface of the watermelon. So do not be stressed about this. So after seeing these models, we should raise two questions. why does only a fraction of the total dose reach its target? This is often answered by pharmacologists who study upon how much concentration of a drug is actually effective in our body. Because sometimes, for example, even though you inject it inside your hand, some of them will reach your brain. In fact, because the blood-brain barrier, less than 1% of the drug is still barely able to enter our brain. So that's the reason why there's been many research in terms of opening up the blood-brain barrier. For example, ultrasound therapy, which is one of the examples, is high-intensity focused ultrasound, which focuses on a specific section of the wall of the brain and also try to widen the gap in order to let the particles go in and let the work do. So another question we could ask is, how should we dose or the administration route of the drug, and how many times or the frequency we should do in order to maintain the drug at the target specific site. So basically, we're trying to look at the efficacy. For example, for this one too, say like there are multiple ways that you could do in order to treat the same one. For example, again, like chemotherapy, it can be either like some of them I don't think they're still therapeutic yet, but there has been some developments in terms of drugs eating them orally, but the thing is the oral route is very, very different from intravenous route, which is literally you put it inside your bloodstream, because one is much more effective at being absorbed than the other. So let's look at the basic administration and the analysis of how the drug movement is measured. For this one, we're going to use a common lab animal called rodent. Many of us use the albino, and some of you who are actually going to college or have experienced in the in situ lab would understand this more, probably equal or more than me. So there are multiple administrations that are used in order to put the drug inside your body. For example, you can do intravenous, which is again putting inside your vein, interpercutaneous. Sorry. So and also the other ones could be subcutaneous injection. For subcutaneous section is the layer between your skin and your muscles. So that's there are other technicalities. For example, which angle should you put the syringe in order to reach that specific point? But that's not going to be discussed in this one because again it's very introductory. The conventional way in order to measure how much of the drug is inside the bloodstream, in this case, as you can see in the image, is by measuring 1-to-1. So basically, as you can see here, one mice gets one specific drug, and his blood is tested, and then it's analyzed. This is a multiple procedure, so I'm not going to discuss much about it. So, but there has been some developments, and one is called cassette dosing. So, as you all know, cassette has like multiple cassettes in one specific pack. So it's also called as N-in-1 dosing. So multiple drugs are going to be simultaneously injected inside one experiment animal, and then its blood will be tested out in order to report the concentration change in those 5 drugs simultaneously. So we usually isolate the drug from the fluid of the animal test, or humans, usually from plasma, plasma is also called as blood. It's kind of different, but you can later search it later. So for this lecture though, we're just going to simplify it to plasma and drug are quite equal. Well, there's one terminology you should know, that plasma is not equal to serum, but that's all you just have to know for this one. So once we isolate the plasma from the vein of the animal, we then use the high-performance liquid chromatography, which is basically making a gradient on the weight scale, molecular weight, and we're going to separate the molecules based on their weight. That's also used in order to collect the supernatant, or more like remove the adjuncts like red blood cell, which could create an invalid data from later analysis. So after that, we're going to use something called tandem mass spectrometry. So it's a very complicated process. It uses ionic reactions too, and also more like shooting the ions. But we're not going to discuss this because it is very technical. But anyways, the main point is that this is the procedure that's commonly used in order to analyze the concentration of each analyte inside an experiment, animal, or humans for clinical trials. Okay. So the two main administration routes that we use is intravenous, which is IV, or PO, which is okay, so PO and also IV. So basically so PO, as you can see here, like later, is about oral injection, while IV, as we all know, is a blood one. So we're going to for here, we're going to see the concentration in the time curve, which is what pharmacokinetics is supposed to be. And this is a common graph that's used to measure it and to see it. And this one is particularly looking at the concentration of the antibodies inside. So, and also, I believe that this is an IV because you can see here it's going directly down instead of like going up and down. So like we want to discuss this later, but it's quite important for you to take note, at least for now. So usually there's a big loop here because it's called an absorption phase, where the drugs are slowly being absorbed inside by the body. But as you all know, in the previous slide, we're directly measuring the blood concentration, the concentration inside our plasma or blood by literally taking the blood itself. So since our administration route and our site of collection is the same, we don't have any particular absorption phase of growing up slowly. Now, this is different from oral one because now you can see that there's a growing change. So the concentration maximum is calculated by the extrapolation when the administration time or the dose time equals 0. And this is because we can't precisely measure the concentration right after the drug is being injected inside our body because, well, it dissipates like almost immediately. So the terminal phase for here, what we call as T1.5 here in notation, is called the true elimination half-life. For those who don't know about what elimination half-life is, so by reading at the slides, we know that it's a time it takes for the concentration of the drug to decrease by half inside the body. This is really common for those who know what just ordinary half-life is. We usually use it for radiology too. And it's very important for the pharmacologist to understand the biodistribution efficiency. So basically how well the drug spreads inside our body. And it also helps them to understand the right dosing interval. So basically how much drug should they put and how much time interval should they do like after one specific drug, because, well, you need to have a constant effect of the drug over a long period of time. And notice that how this is very similar. This line is very similar to the first order chemical reaction, reversible ones. And for those who are taking chemistry, you'll be very familiar with this one. So if you can notice here, we're also using this specific half-life formula. And also we notice that this is slowing down at a specific constant rate, which is K. So from here we can know that there's a very high similarity between a normal chemistry and the biopharmacology. Oral injection in the other way, as I said before, they're quite different. So for here, this one, I'm going to explain briefly what's happening here. So first, the drug is being absorbed by the body. Once it reaches a peak concentration, which is the highest concentration possible inside our body, it then slowly goes down until it just goes to virtually 0. So there's a range, as I said before, the effective range where there's a maximum safe concentration and minimum effective concentration. So in this range, the drug is very effective inside our body, and from the minimum one, the height that the peak concentration has is also called the intensity, or like we would say the maximum intensity or so. And as you can see here, the intensity is similar or look or shows the efficacy of the drug. And the therapeutic range is also looking at the safety one. So for example, very toxic drugs will not have as wide therapeutic range as non-toxic ones do because, well, toxic ones you shouldn't get a lot of them in the first place. So usually absorption is very much faster than elimination. And this is also notated as K of absorption, which is A, is much greater than K of E, which is elimination. So here, as we can see here, the concentration maximum, and also we can see that they slowly go down in this graph. But what this is telling about us is that, as you can see here, the blue line has a much shorter absorption phase, while its elimination phase is much longer. But the thing is that as this goes down and down, the concentration maximum goes down, and also for this one, the time of maximum concentration also increases, which means that drug is being absorbed much slower, and this means that the elimination phase will be shorter compared to when it was very short, when the absorption phase was very short. So the phases have something called compartmental modeling. So usually we use something called two-compartment model. So basically before administration, in which the drug is not present, the drug in the body or specifically in the organs immediately after the administration, and then the drug inside our body after getting in distribution equilibrium, which means that the excretion and the absorption are at equilibrium. It's also called as alpha and the beta phase. So the rapid distribution to the highly perfused tissues, basically when they are rapidly diffused inside the organs, we sometimes call it the distributive half-life of alpha phase, which is, as you can see here, a very rapid one. And then once it's rapidly distributed, then it goes on and very slowly it gets dissipated inside our body and get eliminated, for example, by kidneys. And this is called elimination half-life or beta phase. So combining these two, for those who are majoring in chemistry, this may seem familiar to you. So this one reflects the appropriate Euler number, which means that the derivative is going to be the equal one to this function. And this is important because by combining these two in this appropriate format, which this constant A and constant B are not determined, and they're going to be purposely measured in order to be in a constant one. So from here, this one can show us how the drug's concentration is changing inside our body, and it's called the sum of exponential modeling, or in the first order. So if you have any questions, we're going to skip because this is a video lecture. Now we're going to talk about, wait a minute, now we're going to talk about the multiple dosage and determining the accumulation with the integration of area under the curve, which is also called SAUC. So usually when the drug gets inside our body, this is how a one dose of a drug, so one input of the drug moves. So as you can see here, you can see the small absorption phase and then some elimination phase. This is extrapolated because it's not as it goes. So after that, we again inject it. And notice how for this one, the height of here, the intensity, is almost equal to this one too. So it makes sense because, well, you're inputting with the same concentration usually. So, and here, this area, at least for the first dose, this whole area, the extrapolation 2 included this whole area of the drug's movement and the concentration change is called the area under the curve, which is quite direct. But for the steady phases, it's simply like this much. as you can see in my mouse. So it's not very much compared to this one, but it makes sense because, well, if you do it like this, then it's so bigger. It's like not comparable to the initial dose. That's the reason. So you can see here that although it uses the same drug in this case, the concentration in overall changes for this one. This one goes down, and this one is equal, and this one just goes exponentially up. So why is it? So this is often called accumulation. So you can just visually see that for this one, the drug is accumulating inside our body because they're not going down as quickly as it goes up, the concentration, I mean. But for this one, the patient is seemingly disposing the drug much more efficiently than he or she absorbs it. And for this one, the patient has achieved the equilibrium between getting the dose, the correct interval, appropriate interval, and maintaining it in a specific concentration. So in order to mathematically prove that such accumulation or deaccumulation exists, scientists use the calculus in order to measure the area, calculate the area under the curve for the first dose, which is called area under the curve, AUC for day 1, and then they compare it and make a fraction with the area under the curve for a specific date where the drug was injected. For example, this one. And this is in hours, and this is in days. Sometimes people use different notations, but that's all. So as you can, just a simple example. Let's go here. So as we all know, if the area under the curve for the day 1 is going to be like this, and it's equal to this, which is day 1, then it means that it doesn't accumulate, or it doesn't also go down. So we also call it as ATSS. But what if the area under the curve is less than 1, which means, like, as you can see here visually, compared to this area is much more smaller. So this is also called induction, which is an additive phase where the drug is getting used to the drug, and the body is getting used to the drug, and just disposes it more quickly. So for example, like cytochrome P450 is often used to degrade the drugs, and their levels are increased in the serum of the patients who have inductive response. It just means increased metabolism, so it's not really a big deal. So for this one, the green one though, as we can see here, the area under the curve is very, very large compared to the steady state. So now we can just intuitively see that the ratio between this one and the initial one is much larger than 1. So now this one we call as accumulation, or CLP. So it also means saturated. The last topic I will want to talk about, I assume it's not working well. So last one I want to talk about is called Drug Accumulation Index, or RAC. So we have 2 models, and this one is where we're going to go a little bit deeper inside the mathematics. So Drug Accumulation Index is the index in the extent of the drug accumulation. So it really depends on the drug type and the dosing interval. So why? Well, drugs have multiple functional groups, and also their size really plays a lot of role in terms of getting exposed or not, because when the drug goes inside your kidney, there's a specific filter where it measures the size or the density or the molecular weight of the drug, and then depending on which range does it goes inside, it either dispose or filters or just let it go. And also, some of the drugs are more complex than others. Then if they specifically target a specific receptor, for example, then they will be much more responsive than simply just any kind of drug that just goes inside your body and just waits to be absorbed by the cells. And dosing interval is also important because, well, even though the drug is very foreign and also it accumulates inside your body a lot, if you have, say you have 10-hour interval, then of course the drug is going to slowly, although it's going to slowly go down, and elimination one is going to be really slow. But still, it's going to be going down compared to if the dose interval is going to be like 2 hours. So there are two models that I would like to discuss with you. So the first one is the area under the curve ratio. So basically, it's kind of similar one. It's kind of similar to this one. And this one actually uses calculus as like a note because, as you all know, extrapolating and also calculating this graph equation, it really needs a lot of like mathematical process, but also integrating it and making it into an area formula, that takes calculus a lot. So RAC is also expressed as AUC on area under the curve for T and AUC for infinity. So AUC infinity is the total area of an extrapolated curve from T equals 0 to T equals infinity for the first dose. As I said, here is the initial first dose. It's equivalent to area under the curve for day 1. So area under the curve for the T is simply for a given time T and T plus capital T for this one, which is the capital T means the dosing interval. So it's basically what I have just talked about is the area under the curve for specific dosing interval. Okay, so the steady state is when the absorption and elimination creates dynamic equilibrium, and the dosing interval, as we all know, is the number of hours between the administration. Okay, so the second one is called logistic-like mathematical model. So I didn't make that up because the form actually really resembles logistic model. So basically, by the very definition, for K in hours is the elimination half-life, and T in hours is the dosing interval. The RAC is measured as the concentration, infinity maximum, and concentration when, well, the dosing date was first, maximum. So this is kind of similar to this one. It just shows in a more specific mathematical way. So it's expressed as here and also here. I'm not going to really discuss much about how they derived it because we don't have much time, and also it's very complex. But in simple ways, so basically the drug accumulation index is going to be in this equation where K and T are already explicitly said in the previous sentence above. The challenge I have for today for you is finding the elimination half-life of a drug called XCX without graphical approach. So this figure is modified from an article that I found, and the figure is found from the, okay, I actually forgot the site, but anyways, the most important one would be so anyways, I got the permission to use this graph, and there are multiple information shown here. For example, the dose interval is 12 hours, and this is the steady state, as you can visually see, and well, the RAC is equal to 2, which yes. And the conditions are the elimination half-life is not marked on the graph, and the AUC, which the infinity one, which is literally this whole one, is equal to around 1,500, and the area under curve for 60 to 72 hours is equivalent to around 3,000. So it's, well, in intravenous administration because the curve shape, and the dosing interval, as I said before, is 12 hours. So every dose will increase the concentration of drug inside the blood plasma by 100 micrograms per milliliter. So in case you don't know micro, the micro is when you say meter, what is a millimeter? Millimeter is 10 to the third power, and this is adding another 10 to the minus third power. So basically, 1 microgram is equivalent to just 10 to the minus 6 power of a normal gram. So pause the video if you would like to try to solve this with these two equations that I've shown you. Okay, so it's very simple. The first one, as we can see here, we are already given two critical informations. As we see, the area under the curve for the steady state is 3,000, and the area under the curve for the first dose is 1,500. And we know that RAC is equivalent to the ratio between these two. So we then just calculated, and I purposely approximated for simplicity, and from that we can see that the RAC is around 2. The second one we're going to use is the logistic-like mathematical model, which is R equals this. So we already know that K is the one that we want to find. But the other variable T, we already know it. It's 12 hours. It's already given. But the thing is that we already know, again, that RAC is equivalent to 2, or similar to. So from here, we just use simple algebra. We just put it in, substitute R with 2, and then we move the denominator, multiply it together, move it, and then after simplifying it and also putting the natural log in order to remove the exponent, the Euler number, then we can find the K equals the negative of natural log of 1/2 divided by 12. And this is around 0.05776 hours. But it's kind of weird to see this result. Because as you can see here, the half-life should be around like 50 range, which like visually looks like it's 6 hours. But yet we have 0.05 hours. So why is it wrong? First, there's a theoretical model. So as we know that these two are simply when drug moves in a complete ideal circumstance. But patients have different physiological conditions, and that may change the drug response. And also, like, just remember that this is just a theoretical model provided by an article. This is not an actual one, so it also makes sense that this doesn't portray accurately to some degree. So another one that's wrong is that the AUC, area under the curve estimation, is quite deviated. Well, we just estimate this around 1,500 and around 3,000, but we don't know whether it's going to be actually like that. But it's not substantial, but the main point is that this is all theoretical. So in real life, it's going to be much more complicated. You need to put a lot more factors, but this I hope that from here, although it was quite chaotic and also we had multiple topics to go over, it was I hope that you learned quite some, or at least some interesting topics about the pharmacokinetics. I'm Charles Shin, and thank you for listening.